Hello everyone, welcome to 369 Chemistry, and as the topic suggests, in this video we are going to talk about your factors affecting crystal field theory or crystal field splitting energy. Okay, so the energy which is required by the d-electrons to split up, or you can say when the ligand approaches the d-orbitals, it gets split up and into T2G and EG level. So that energy difference depends on various factors. So what are those factors? We are going to discuss in details. Affecting the magnitude of your crystal field splitting energy. That means that crystal field splitting depends on what factors. Okay, which complex will show your higher spin complex, and which one will show low spin complex, and which one will form tetrahedral, which one will form octahedral, and what are the factors depending on which they actually form. So that we are going to do in this chapter. Okay, so the first is your geometry of the complex. Okay, so your crystal field splitting of your square planar is more than your octahedral, and is more 1/3 of octahedral, and this is your octahedral, and this is 0.45 of octahedral splitting. Okay, this way it varies. So what is the explanation? In octahedral complex, what happens is that you can write all these things in the examination. You will have to write the similar way only. Okay, so in your complex, the splitting of the orbital is more than twice as strong as in your tetrahedral. Okay, for complexes of same metal ion and the same ligand. Okay, for same metal ion. Okay, that means for same metal ion and your same ligand. For metal ion will be same in for the same ligand. Octahedral complex or splitting is more than your tetrahedral, and then in octahedral splitting, six ligands are involved. Whereas in your tetrahedral splitting, only four you can say ligands are there. So this results in your 33% decrease in field strength. What does it mean? It means that provided all factors are not changed, provided other factors remains constant, it says that if your, because it has 6 ligand in octahedral splitting, okay, and in your tetrahedral splitting you have only 4 ligand, right? You have only 4 ligand out here, and in your crystal field splitting there's 6 ligand. So 6 ligand, more is the number of ligand, more number of ligand, same metal ion and same ligand, so more field strength, which is equal to your more splitting. All right, so in this case this is the thing. And number, okay, your in octahedral splitting, what happens in your octahedral splitting? Your dz square and your dx square minus y square, these the ligand approaches directly. In this direction of dz square and dx square minus y square, that is your EG set. So hence more splitting. Okay, then your dxy, dyz and your dzx, they face less repulsion. Okay, so that's why they are directly. That means in your octahedral splitting, what happens? There are how many ligands? There are 6 ligands, right? So in this octahedral splitting, what happens is that they approaches directly the lobes. of your dz square head-on collision takes place, hence more splitting. Whereas if they are approaching, the ligands are approaching dxy, dyz and dzx in case of tetrahedral, so they are making an angle. Okay, so directly they are not even not even coming to the axis. These two are the axis and these are your planes, so they are directly not facing the axis but they are facing the plane. So at that time what happens, the splitting decreases. Okay, so the second factor is that your nature of ligands. Nature of ligands, that means, is it weak field ligand or strong field ligand, or strong field ligand? So what happens if it is a weak field? In the ligand having higher splitting power, okay, you write like this. So which one will give you high CFSE or low CFSE also depends on the nature of the ligand. Weak field ligand will give you high spin complex and your tetrahedral complex, or you can say low crystal field splitting, whereas a strong field ligand will give you more splitting. Okay, the ligand having higher splitting power, that is your stronger ligand, gives more splitting, whereas weaker ligand gives low splitting. So what are the series? See, I minus, your Br minus, your NO3 minus. This way, this is the chemical series where the ligand field strength increases. Please remember this or write it down so that you can have a look before going to your competitive examination. So which ligands are stronger? These are your weaker ligands. Okay, they are going and forming more stronger. C2O4 2 minus. Then is your water, NCS, PY, ammonia, En. Now we are coming to your high splitting ligands, okay, which are bidentate or polydentate ligands. These are also called your high, you can say, strong field ligands. Carbon monoxide, these are your strong field ligands. So this way, and these are your weak field ligand, and this is your strong field ligand. Okay, so I will give you an example. There is an example of delta naught value, that means crystal field splitting energy of Ni Br6 4 minus comma Ni Cl6 4 minus comma Ni H2O whole 6 2 plus Ni NH3 whole 6. These are all strong field ligands, and your nickel En whole 3. This is again your 2 plus. All these are your nickel 2 octahedral complex. Okay, here see, the central metal atom is same. These are all nickel. Okay, for the same oxidation state, for the same metal ion, there are different ligands. If we use different ligands, then we are getting different rate of your splitting. Okay, so what is the now the which is the most weaker ligand here? It is your nickel bromide. Okay, then nickel chloride, then comes water, then ammonia, then your ethylene diamine. Okay, so this way the thing increases, so delta value increases also in the order. The first one is your 7,000, then 72,000, then comes your 8,500, then comes your 10,800, then comes your 11,500. Okay, so this way it is increases. This one is of your nickel Br whole 6 ligand. Field strength increases in the order. Br minus cannot split much. Cl will split some more, water will split more, then ammonia strong field ligand splitting is more, and the last one En, because this is your ethylene diamine, splitting is most instances. So delta naught value increases. Okay, first one, it depends on geometry. Second, depends on the nature of the ligand. Then we'll go the third one, which is your, okay, the third one is your nature of central metal atom. Central metal atom. That means first we talked about the nature of ligands, then we talked about the geometry of the complex. Now we are talking about the nature of your central metal atom. That means if you go down the series, that is from 3D to 4D and 5D, so the splitting increases from 3D to 4D, 4D to 5D. Okay, so delta value increases, okay, from first transition series to second transition series and to third transition series. Why so? Yes, there is an explanation why. See, delta naught value increases as we move from central metal ion from 3D configuration to 4D and to 5D. Thus, the value increases with the increase in the value of principal quantum number. So, with increase in your increasing principal quantum number, splitting increases. Splitting of the complex increases. Okay, so why so? So for example, if we take we will take the example of cobalt 3 plus, rubidium 3 plus, and your iridium 3 plus. These belong to your 3D series, this belongs to your 4D series, and this belongs to your 5D series. Okay, so if you take this complex, the cobalt ammonium complex of octahedral, then your RH NH3 whole 6 3 plus, and your IR ammonia complex, if we take by experimental analysis, what did we get is that as this one we got as delta naught values of this is 2300 splitting, and here it is 3400, and here it is 4100. So as we move down the group, what happens is that the splitting increases, the orbital splitting increases. Why? Because it is more due to the larger size of your 4D and 5D orbitals are likely to interact with the ligand more effectively than your 3D orbitals. On moving down the group, nuclear charge on the metal ion increases. This increased nuclear charge may also have an effect on the magnitude of your crystal field splitting. That means as we go down the group, what happens is that nuclear charge increases. As I said, atomic number increases, nuclear charge also increases. So that time what happens, we know something called your inert pair effect also, right? So these electrons on the 4D level or your 4D levels or your 5D levels, they are more diffused. So the ligand orbitals are more likely to interact with your 3D orbitals. But on moving down the group, the nuclear charge on the metal increases. This nuclear charge may also have an effect on the magnitude of splitting. Okay, go down the group, you can write it in the exam, like you can write in your copy, due to their larger size, 4D and 5D orbitals are more likely to interact with the ligand orbitals as we go down the group. Okay, so more effective splitting. More effective than your 3D orbitals. Okay, on moving down the group, nuclear charge also increases. So this charge, which is your positive charge, now this forms more splitting with negative ligands. So I'll summarize this. As we go down the group, what happens? The size increases. Size increases, that means electron is more diffused. If electron is more diffused, that means now the ligand can easily come and approach, and they can form more interaction is taking place than your 3D orbitals. They are not, they are more closer to the nucleus. So what happens is that the splitting, or you can say more interaction, does not take place in 3D orbitals, whereas in case of your 4D and 5D orbitals, splitting can be more, because more interaction between the ligand and the 4D orbitals and 5D orbital takes place. Plus there is a nuclear charge increasing. So what happens is that this nuclear charge, positive charge, can have an electrostatic attraction towards the negative ligand. Okay, so what is that? There is a increase in the energy, so crystal field splitting is higher. Now we will go for this is when the central metal atom, about the same oxidation state, central metal atom. Now the central metal atom with, you can say, with different oxidation state. That means here what happens is that central metal atom, okay, with different oxidation state will be explained. For example, if I'm taking the example, I'll take the example of Mn2 plus and your Mn3 plus. Okay, as the charge increases, so crystal field splitting will increase. Here it is your +2 oxidation state, here it is +3 oxidation state. Here this crystal field splitting we found to be at your 8500, and here it is 2100. Okay, so what we can say, as the charge increases, delta value, or you can say crystal field splitting, also increases. What is the explanation? The explanation is that as delta value increases, that means as the crystal field splitting increases due to substantial increase in sigma bonding. Sigma bonding. Here the word came to be sigma bonding. Why? See, when the oxidation state increases, sigma bonding also increases. As the charge increases, sigma bond becomes shorter and shorter. Why? Because as the charge will increase, that means it is losing electron. Is it not that its size will decrease? Right? So sigma bonding, which is because of the decrease in the radius of the metal ion. So as the radius of the metal ion decreases, what increases? Why? Because here what happens, the metal ion now, the metal ion having increased charge attracts the ligand towards itself more strongly, and hence the splitting of the orbitals takes place to a greater extent. Okay, as the positive charge increases, so there is more strongly, it pulls the ligand towards itself, and hence your greater splitting takes place. Okay, greater splitting give your higher value of delta. Last is your, when central metal atom of different metals, when you have different metals with different oxidation state, so what you will do in this case, the oxidation state, when the oxidation state is different for different metal atom. So if we say, we will first take the example is your vanadium 2 plus and chromium 3 plus ion have +2 and your +3 oxidation state. So delta naught value of vanadium 2 plus and chromium 3 plus here. So it is complex ions. What it is shown, this is your +2 oxidation state, and here it is +3 oxidation state. Delta naught value of this is found to be 12,400 experimentally. Okay, and this one is found to be your 17,400. What is the explanation? Explanation is that the increase in the value of your delta naught with the increase in the magnitude of the oxidation state of the central metal atom, and this is because the fact that central metal atom with the higher positive charge has greater attraction for the ligands, and hence the ligands can approach the central metal atom more closely than they approach the central metal atom in ion with lower positively charged. Thus the ligand exert stronger crystal field splitting effect on the orbit electrons of the central metal atom with higher positive charge and stronger crystal field splitting magnitude. That means what it is saying is that you can say with if higher charge, higher oxidations with the higher oxidation state metal will pull the electrons of ligand more effectively than the metal atom with lower oxidation state and hence low splitting. Means if the oxidation state is higher, see here, if it is +3, that means 3 electron loss, the size is smaller. So now what we will do, it will try to take up more electrons from the ligands, and it will form more it will bind with the ligand more effectively, so more splitting and the energy increases. Whereas in this case the charge is less, oxidation state is less, so the effectivity of bonding of this vanadium with water molecule is still lesser than with your chromium. So this is your answer, and I have finished with completing your factors affecting your crystal field splitting. This is very important topic. Why? Because based on this only they give you competitive examination, and you cannot answer it just because you don't know the basics. So basics is more important. Concentrate here so that you can complete your competitive examination quickly and easily.